Hello, my name is Haithem Turki, and the title of my project is Speculative Wizard for Edge-Based Interactive Image Search. And so my project builds upon existing work that was pioneered by Professor Satya's research group called Eureka. And Eureka is a platform that allows users to do interactive content-based search of unindexed visual data. One of the target audiences of Eureka was domain experts, so folks that have valuable knowledge that is not easy to outsource. And kind of the idea is that these experts might want to try to find interesting images to train an image, to create an image training data set, for example, but these users may not have deep programming experience, and are especially in the domain of computer vision. And so what Eureka kind of aims to do is allow these users to create these sequence of filters via point-and-click interface in a GUI that allows them to quickly kind of hone in on images that may be of interest to them and identify images they might want to collect. And so kind of where my project comes in is that we discovered that oftentimes these users will discover the optimal sequence of filters through a lot of iteration and a lot of trial and error. And so the goal of my project was to find ways of having the machine help. One specific idea we had was to see if the machine could proactively suggest filters that may be of use to the user. But we also broadly wanted to see just various methods to improve and make the overall iteration process more efficient. And so to kind of put this into context, say I am an expert and I'm trying to find images of helicopters. It so happens to be that there are various off-the-shelf neural networks out there, such as MobileNet, that already have a plane classifier that could be of use to us. The issue is just that this classifier is very broad. It contains not only helicopters, but it contains jets, military planes, and a whole bunch of other stuff that may be irrelevant to the user. And so what the user would traditionally do of Eureka is they might select some examples of helicopters, and they might try to select patches and use this to train a new filter to add on top of their existing MobileNet filter. So here, for example, I might be adding this to a hog SVM filter, and I'll add a couple more examples for completeness. And so once I add enough examples, the user, in the traditional Eureka workflow, what they'll have to do is they'll stop and restart their search, and this time the search will run against both filters in the sequence. And a thing to note is that searches in Eureka, they're currently quite transient. Once you stop an existing search, you kind of lose access to that search. So you have to be pretty careful in terms of figuring out when you want to launch a new search. What's more is that this process was relatively manual. I had to select some image patches, and I chose hog, and it might happen to be I chose the wrong image patches, or hog was just not a good classifier to start with. But as you can see, our set of filters does not seem to be particularly good. It does not seem to meaningfully reduce the signal-to-noise ratio of this search in terms of finding helicopters. And so in contrast, going into the work that I did over the semester, instead of having a user manually select patches and manually think of what filter might work, we're just going to restart that search and instead just have the user manually select examples. So we'll say this is not a helicopter. We'll say that this one is. And we'll collect a couple more just for completeness. See if there's any other helicopters in the set. So as you can see, there's quite the signal-to-noise ratio is quite high initially. We'll collect maybe one or two samples. And what's basically happening is that in the background, as I'm labeling examples, the computer will basically be, the server will be training a collection of models in the background, and it will incrementally improve, create new models as I continue labeling examples. let me maybe try adding one more example here. So we'll say this is a negative. See if we can find one more image of a helicopter. Anyways, so we'll say that we're happy with our filter. And so what we'll get is this model statistics window will show that the machine is suggesting that transfer learning may be a good classifier to use. It will show us kind of its predicted accuracy, and if we're happy, what we can do is we can add this in one click as a new filter in our stack. And what's more is that if we want to get additional validation before committing to a new search, we can click this preview results button. And what this preview results button will do is it will run the updated filter stack against the existing images that have been returned as part of this search, and it will show the machine's attempt at labeling this data. And so as you can see here now, on top of my existing explicit labels, we can see what the machine is predicting. So you can see it might not be perfect, but does seem to be capturing, correctly flagging planes as non-helicopters and flagging helicopters as helicopters. I might wish to correct various mistakes and label those as well, or I might be satisfied and I might want to run this search for real now. And so what I will be doing now is I'm stopping my existing search and I'm starting my existing search. And although the results may not be completely accurate, hopefully what will happen is that we will get way more images of helicopters than previously, and the signal to noise ratio will be a lot better. So as you can see, we get quite a few images of helicopters now. And this hopefully will allow the end user to be a lot more productive. So hopefully this is a pretty interesting application of what you can do when you marry kind of advancements in computer vision with applications at the edge to create systems that are hopefully more than the sum of their parts. So that's it for my presentation, and thank you very much.